Hey guys, and welcome back to the lab. Today we're gonna set up and benchmark a few open source object stores, and we'll include LabStore in the rankings as well. You'll learn how to do a basic deployment for projects like Garage or SeaweedFS using Docker Compose, and you'll also learn how to configure and run Warp for benchmarking. We'll show you how to orchestrate everything, including the final analysis, which is based on DuckDB and TermGraph, simply by using the Just Task Runner. We'll also cover end-to-end profiling in Go, where you'll learn how to set up pprof and how to analyze the results in a way that is useful to identify bottlenecks and to help you improve your application's performance. Let's dive right in. So we selected a few object stores to include in our benchmark. Of course, we are including our very own LabStore in the rankings as well, so that we know where we stand at the beginning of this project, although it's still very early. We are including MinIO as well. We are using the latest version that is available as a Docker image. As you know, they no longer build their own images, although the project is still openly available but not maintained. We are also going to include Garage, although we are going to use a single node, single drive for all our deployments, and so it might not completely do justice to some of these object stores, but they are all in the same level when they are being evaluated anyway. We are including SeaweedFS with their S3 API, their S3 gateway. They also support this. And we are including RustFS, which is one of the hottest ones in terms of performance right now. And I can tell you it is ranked really high in terms of performance, although it's not the highest one, and we'll get to that. We also considered Ceph, because Ceph can be used with their Rados gateway, which provides an S3 API. They also have an IAM API, which is pretty cool. But Ceph is a bit harder to deploy, so it wasn't justified for us to put so much time into getting it running just for a benchmark. We also found this VitaStore project over here. We didn't include it because of time constraints, but this might also be an interesting option. And we also found Zenko Cloud Server, which provides an S3 API as well. And we also did not include this, so we are going to look at benchmarks for LabStore, MinIO, Garage, SeaweedFS, and RustFS. So now let's look at the deployment for each object store, and as usual, this code is available as open source within our LabStore repo. If you go into infra, you'll find the compose file, and this compose file as well as some Docker files. This will include everything that you need for the benchmarks. It will be under this benchmark profile. And you also have a just file that will help you set this up easily. And so we've got our entry point for our front end, our entry point for our back end, and this is not a part of the benchmark. And then we get into the benchmark for LabStore, which is our back end only. We now have Docker deployment. This is not published as an image yet because we haven't released even the 0.10 version yet, so it's not ready for everyday usage, but we are for now building it over here. So if we take a look at our Docker file for the backend, it's a very simple Docker file which has got multi-stage building. It's got a builder stage and the deployment stage. As you can see, we are just importing from this Golang image based on Alpine. We build for the target OS. We use the image for the platform we are running Docker on. And then we just switch to a work directory. We copy the go mod and go sum into that directory. We download all modules, and then we copy the code, all of the code into the directory, and we compile this for the target architecture, as you can see over here. And then once we are done with compilation, we create a clean image from Alpine where we copy from our builder. We just need the binary, we drop it on user local bin, and we create a group for LabStore, create this data directory, which we will expose as a volume and where LabStore user and group can write to. Then we switch to the LabStore user and use LabStore as our entry point. So this Docker file is essentially the LabStore server command, right? Then on our Docker Compose, we build that Docker file based on the root of the repo, so that we can access the backend and all the other stuff, because we would be running under infra, right? And then we expose this on the set port with the benchmark LabStore port environment variable, and we use a fixed port for our backend within the container. All of these are running within the benchmark network. We've got a benchmark dash name of the service, in this case LabStore, for the data, and we've got this benchmark store access key that we use for admin credentials for all the object stores that we are going to test. For LabStore, we set host to 000. Port is the same as this one. This is our default port, 6789. It's very easy to memorize. And we set storage path to /data as well. Now for MinIO, like I said, we are based off the latest existing Docker image. And then we just do a regular deployment. We don't have a custom Docker file or anything. We expose port 9000. We also export the web UI, although we do not use it here. And then it's pretty similar to LabStore. We set a volume that points to /data. We use the same credentials, and we start the server with the UI on port 9001. Otherwise this will be randomly assigned, and port 9000 is the default anyway. And we also added a health check just to make sure that the service is running properly, and that's it for MinIO. Now for Garage, deployment was not as straightforward as for MinIO or LabStore. We had to create a custom Docker file just for the purpose of copying our config into it. Since we are deploying on a remote Docker host, we cannot really, it is not viable for us to copy this file into the Docker host and then mount it as a volume. And so this config file lets you set the metadata and data dirs, the DB engine, they use SQLite. I think we'll also use SQLite on LabStore. We set replication factor to only 1 because this is a single node and we want to keep it as lightweight as possible. Then we set up everything like these secrets over here and take care that we should keep this safe, both the RPC secret and the admin and metrics token. We are not doing that because we are just benchmarking here, but if you are doing that in production, take care of this. Then we deploy the S3 API into port 3900, and we also expose the web UI on port 3902. And finally we expose the admin service on port 3903, which we'll need to use to set up the admin credentials. There are no environment variables that we can use to do so. So if you go into here, you'll see that we are only using this environment variable for the port. Everything else will need to be done through the Garage command, and we'll get to that later when we are going through the just commands that we set up to provision all this infrastructure. We'll have a garage init command where we take care of all of these user creation and bucket creation tasks. We won't be able to use our preset credentials because Garage requires you to generate an access key and a secret key directly using their command, so it's randomly generated by them. But that's about it. This was the hardest to deploy, although it's not really that hard, but it was just not as straightforward as the other options. For SeaweedFS, they provide several separate services which you can deploy using separate Docker Compose services as well, but they also provide the server command which takes care of all of these services for you with a single command, and that's what you used here. We set the data directory to /data, then we enable the S3 API with -S3, and we set the port for the S3 API to 8333, which is the one that we expose here for the benchmark. We also expose the remaining ports, although we don't really use them here. Now for RustFS, deployment was also fairly easy. Their default ports are the same as MinIO, so we had to use 10,000 and 10,001 instead. They use the /data directory by default for storage, and we were able to use our custom access key and secret key for our admin account. We also enable the console, although we do not use it. Again, I believe this is for the web UI. However, we bumped into a small issue with RustFS when running on our Docker host, which is deployed on a Proxmox VM. And because the VM originally was running with the CPU type x86 64v2 AS, for some reason it didn't support some SIMD CPU features that it required, so we ended up switching to CPU type as the host, and we destroyed and recreated the container, and we were able to run it without an issue. Before that, it was complaining about missing SSE 4.1 as well as PCL mul QDQ, but once we switched to host, it worked correctly. So first thing that we need to do is to provision all the infrastructure required for our benchmark, the Docker Compose file I was just going through with you. So for that we can run just infra benchmark up, but since we are running so we are running on default Docker context, and because we want to be able to test taking into account the bandwidth that we've got on our local gigabit Ethernet, we'll instead use the Docker apps VM. So we'll switch to Docker apps over here, and now if we just infra benchmark up, this will provision everything including LabStore and the remaining object stores, as well as an iPerf 3 server that we are going to use to measure the bandwidth without any load, so we have a baseline. Then if we run, for instance, lazy docker, we'll see that we've got our object stores up and running. Okay, and in here you've got LabStore, and everything is up and running. And also check it if we use docker ps, or more cleanly like this. And now let's take a look at the configs and how we orchestrate everything in here. And so for our benchmark, we've got a just file specifically for handling all of this. And we also needed to create a config for warp, which is our main tool for benchmarking. This is from MinIO. So we are using this in mixed mode, which means that different requests will be done to the object store, and these requests are get, stat, put and delete, and this defines the probability of one of these requests being picked at each time. So we are doing a lot more get requests than stat requests, only 15% of put requests and 10% of delete requests. We are working with 1,000 objects, a concurrency of 8, so 8 parallel requests at a single time at most. And our objects are 100 kilobytes, and we also disabled multi-part just because LabStore doesn't support it yet, so we wanted to make this a fair comparison end to end. And that's about it. This will produce a JSON file in the end, and we use that JSON file to run our analysis with DuckDB. So going to our just file. For our just file, besides regular stuff like checking for dependencies, we also have a command to measure the bandwidth, where we run ipperf3, and this will also produce a JSON file that we use for our analysis. For Garage, we've got a special command to initialize Garage, and so everything that we can do on the other object stores with just 2 environment variables, we'll need to do here with this logic. So we run the Garage command directly from the container, and this is under /garage, it's a binary. We wait for Garage to be ready, checking the status, and once it's ready, for the initial run, we apply an initial layout where we assign a capacity of 5 gigs to this node, set the zone where it runs, and we apply that layout. Then we look for any admin access keys that might have been created previously, and we delete them all. And then we create our own admin access key, and we retrieve the access and secret from the output over here. Finally, we create the warp bucket, which is warp benchmark bucket, which will be used by warp during testing, because we need to grant permissions to this admin access key, otherwise you won't be able to warp won't be able to create a bucket. So we do that by running bucket allow read write owner to the given bucket that we created for the admin access key, and that's it. So once we do this, the credentials will be printed to the standard output, and these will be used for benchmarking over here. So we just run garage init over here, and we extract the access and secret key so that we can create the bucket. We run it with MC first, and then we export our warp configurations, including the host and port, the access key, the secret key, the region, and TLS, true or false. And we set our output there. We cd to warp, we create that output there, cd to the output there, and run warp using the config that we just showed you before, so that the output, JSON output, is dropped. It is dropped by default on the current directory, so it will be dropped on this output directory, one for each object store. We do the same for other object stores. We've got this store command which takes an ID. The ID can be LabStore, MinIO, etc. And we just set up the host. If it's Garage, it will call its own separate process. Otherwise, it will just by default load the benchmark store access key, which we were able to set manually for all other options. And we do the same. We create the bucket, we set up warp to run with these credentials, and we cd to the output dir for each corresponding object store, and run the warp command for benchmarking. So this command just calls all of these for each store. We can also do it for one of them individually. This is very useful for us when testing LabStore. And then we run our analysis. We've got a bunch of helpful stuff, like running a SQL file directly on a DuckDB database from the command line, or printing the output using column as a CSV from a CSV. And then we also plot the results using term graph directly on the terminal, just for easy visualization. We don't need an image here. And so analysis will create an output directory, run the load SQL, and let's take a look at this file. So this is just DuckDB code, and we created a macro for loading for each individual object store, each output. So we iterate, we take all JSON files for that from that directory, because if we run multiple benchmarks, then all the information will be used to calculate the performance. And then we go into BIOP type. We take the value for this key, and then we iterate over each segment, which has got a start date, the bytes per second, and the objects per second for that particular time. And like I said, we create a table called warp stats with the stats for each object store. We load them using warp load in here, and we run a union. And then we also create a similar table for iPerf stats, which just gives us the bandwidth that our network is capable of putting through, right? So the throughput. And then we run our summary SQL, which is the actual analysis. So we've got our summary stats, and we compute medians for everything. So median upload bytes, download bytes for iPerf, and this is our baseline bandwidth. And then we compute the median objects per second, we compute the median bytes per second, and we convert this to megabytes, right? And then for put and get, we also get the bytes per second, and we compute the median over here. And finally we just use row number to rank this by median objects per second in the descending manner. So this is just the best one, is the one that is able to put through more objects per second for each type of request. And then we analyze the results per type of request: delete, get, put, and stat. And this maps directly to HTTP methods, except for stat, which is a head request. And we also drop these results as a CSV that we might want to use later, and we drop these results as well as a single CSV for all operations, and that's how we benchmark this. And finally, we also use our new LabStore YAML config to set up the configs for the benchmark. In here you just set the host where your object stores are running, and then you set the ports for each object store and also iPerf over here. The defaults should be fine if you didn't change anything. And for the object stores we also set the admin access key and secret key, except for garage, which needs to be generated. And we set TLS to false and region to EU West, but it's really whatever here. And so now we can go into the terminal and launch our benchmark. Make sure to benchmark clean if you are running from a different host, because since bandwidth will be different, you'll get different results mixed in. And then you can just benchmark to see everything that is available, all the commands. and the main ones are running the benchmark for a given store or for all stores, and you can also run everything including the benchmark, the bandwidth testing and the analysis by calling just benchmark all, which is what we are going to run now. And first it will measure the bandwidth that is available to us. In our case we are running a 1 gigabit Ethernet, but we are also recording this video, which is taking some bandwidth. Regardless, this should be quite similar throughout the benchmark for all object stores. So now it's running for LabStore, and we are getting about 1040 get requests and 345 put requests per second. So now it is running the benchmark for MinIO, and let's see how many get and put requests we can run per second, how many objects per second, and we are able to run more or less 700 get requests and 230 put requests per second, although the get requests are going down to 680 more or less. Now it's running the setup, the initialization for Garage, as you can see here, and it just created some temporary permissions for an admin user that it is using with Warp. So in here for get requests we are getting a little less. We are getting about 300 get requests and 100 put requests per second with Garage. So this is one of the lowest so far. So the VM where we are running Docker has 2 cores available to it and 10 gigs of RAM, besides the 1 gigabit Ethernet. In here we are running the benchmark for SeaweedFS. As we can see, we are getting about 730 get requests and 245 put requests, more or less. But of course in the end we are going to look at median values instead, so the outliers are less prevalent than they are on the average. So now we are running the benchmark for RustFS, which is known to be one of the highest performing object stores out there at the moment. And like we can see, it can get to 820 get requests and 270 put requests. And once we are done with RustFS, then the just command will keep going and run the analysis, load the data using DuckDB, summarize it using DuckDB as well, and one table per operation will be printed with rankings as well as a term graph chart, as you will be able to see right now. And here we go. So let's go through the results. As we can see, LabStore is doing quite well for all operations, and especially for get operations over here. Okay, but RustFS is a close second, and I say close second because, like I said, LabStore is very minimal. We haven't implemented most of the features yet, and it will inevitably go down, and it even might be second to RustFS depending on the complexity of the features that we implement. We can look at the tables for each operation. So for instance, for delete, we've got LabStore, RustFS, SeaweedFS, MinIO and Garage. We've got forget, we've got LabStore, RustFS, SeaweedFS, MinIO and Garage. So the same ranking as the delete. And I believe we've got this same ranking throughout all operations. It's closer for put requests, but we are still still able to outperform RustFS. And then we've got our stat or head requests, and like you see here, RustFS, SeaweedFS are two of the fastest. I know that many people are going to Garage because Garage has a nice web UI, but a cool web UI is coming to LabStore in the near future as well, so stay tuned for that. And you know, that's it. If you want to run this benchmark yourself, you can clone the repo for LabStore and follow the steps. If you run the just commands, we've got checks to help you determine which tools you need to install, and that's it. You can reproduce this, criticize our approach if you like. I'm sure we missed something in here somewhere, but this will give us a good starting point, and we wanted to know whether LabStore is ahead of the curve or behind the curve, because since it's such an early project, if it was too slow already, that would be a red flag and we would need to rethink the architecture somehow. But we are quite happy with the current results, although they are not representative of the final product yet, because like I said, it's very minimal yet in terms of implementation. We don't have IAM, we don't have users, we only have one user, that is the admin, and that's got no overhead, right, because there are no access policies to handle. So we'll need to add a SQLite database to store all those policies, and that will introduce slight overhead, maybe not that much, but we'll see when we get there. Now the process is set up, and we've got other processes to help us keep performance up as well, and we'll get right into those now. So now let's switch topics a little bit and let's go into profiling in Go. And this time we are going to focus on LabStore only, but you can do this for your project as well. So you'll learn how to set up pprof to profile your software for a fixed amount of time, collect some data, and of course you have to make sure it's under load somehow for the feature that you are trying to test performance for. But there's a few steps to set all of this up, and I'll go through them now. So first thing you need to do, and let's go into the backend, you need to run a service within your Go code so that the profiler can communicate with your code, right? And one way, or the way you can do that, is by importing net http pprof, and you just start a service normally on port 6060, and we use this Go routine to launch this in parallel because we've got our own service also running. And we only start the profiler if we use a particular flag in the command line. So if you go into here, you'll see that we've got our pprof flag, and if it's set, then we can specify a host and a port that is different from the default if you like, and we create this new profiler and start it, right? Besides our already regular service that we start under serve. So once this is started, you'll need to run gotool pprof and connect to the port 6060 on your application in LabStore in this particular case, and give it a duration for which you want to capture data for, and then put your service under load so you have data to look at. So we set this up on our make file. So if you go into our make file, we've got this make profile over here. We are using npx concurrently because we want to launch two services. One of them is our backend with the flag pprof enabled, so that profiler is enabled. It uses port 6060. And the other one, and let me just do this so you can read it. The other one is calling Go tool pprof, which comes pre-packaged in with Go. And then we use this focus to filter profiling for our particular code types and functions. So functions to be precise. So we want to look at package github.com Illumino Labs LabStore backend, which is our package. And once we are connecting to localhost 6060, which is where our profiler is running, we call this debug pprof profile, and we ask for it to collect data for 60 seconds. Once the 60 seconds are up, it will automatically open your browser on port 8081 in this case. Most commonly it's 8080, but I'm already using 8080 for something else. So and this is how you profile. So what you do to run the profiler is essentially run make profile, and for instance run the benchmark on top of LabStore, wait for 60 seconds, and then we'll get some data. And so let's run our profiler for LabStore. First let's split this into two, and once we start make profile, we need to also start the benchmark right away because we've got 60 seconds to capture data. And also let's go into our config and make sure that this is localhost and that we are using the default port for LabStore. And now let's start our profiler and let's run our benchmark. As you can see, we are getting a lot more get and put requests because this is now running locally, right? And once this once the 60 seconds are up, the browser will open up with a web UI where we'll be able to analyze the data that was collected here. Keep in mind that the benchmark is not tied to the time that the profiler runs. So once the 60 seconds are up, your browser will open up with the results regardless of whether the benchmark is still running or not, right? And there we go, the browser has just opened, and this is how the results from profiling look like. So it will open on the graph view. We've got multiple graphs, but it opens on the graph view. And in here you'll find functions, the time that it took for it to run, so the time that it took inside this particular function directly, as well as the total time including calls to other functions below. And as you can see, we've got the logging middleware taking quite a lot of time in here, and the auth middleware taking some time as well. We've got put requests taking more than get requests, and etc. But it's much easier to understand exactly where time is being spent if we go into the flame graph view. So with the flame graph view, you'll be able to see that everything starts from root, serve, and then you go through the middleware that we've got. And as you can see, the auth verify SeaweedFS, which is just the authentication with SeaweedFS, is taking quite a slice, and logging is taking a smaller slice, but both of these are larger than the slices we see here for let's see what this is, for delete requests and add requests, right? We also got put requests taking the most out of all requests, and then get requests. If we need to inspect one of these, we can click it and we'll see exactly where most of the time is being spent. And in here we already have some useful information. So we've got this security trunk param header function, which is only used for logging when debug mode is enabled, and right now it's not enabled, right? And it's still taking quite a slice out of SeaweedFS verification. So this means that we are not running this properly. This should be called lazily, so that it's only called when debug is being printed, debug messages are being printed. So this is an obvious one, and it can very easily save us 50% of the time that we are spending on authentication right now. So this was already quite productive. We can go back to the original view by clicking root. Let's see how what the logger is doing as well. And as we can see, the handler is the one that's taking quite a while, and particularly writing. So maybe we are using the tint handler for color logs. Maybe we can try to use regular text logs and see if there is something different, and we might make this optional so that when we deploy LabStore in production we disable colors. We don't need that anyway for cloud environments, and probably we will also use JSON logging anyway, right? So we just need text, so we might be able to improve performance in here a bit as well. If you go, for instance, into the get object, can we improve anything over here? So most of the time that we are spending is on copy buffer, and copy buffer is reading from you know, the object that is being uploaded. So there is a limitation there due to bandwidth and disk IO as well. So we might be able to improve this slightly, but probably not that much in here. Let's just take a quick look at put as well to see if it's different or not. It's quite similar. So if we are able to improve one of them, we are probably able to improve this as well. We can also see that for put requests we are verifying each chunk. So if we can improve this, we'll also improve the put process, but I believe this is already maxed out, so we probably won't be able to improve this much more, besides something that is really tiny, like replacing with a high performance library that computes SHA 256 or something like that. But you know, that's how you do profiling in Go. Hopefully it's not that complex to you now that you've seen how you can set it up, and hopefully you use it more, because the way I see it, the tools that we need for the development are a good debugger, which not all people use. Some people do prints instead, which is a much slower approach, and you are actually doing the same thing you are doing in debugging. So if you don't know how to debug, you should learn how to debug. And also, and this is something that is less common, is to use a profiler so that you optimize the performance of your software. This doesn't mean that you need to do any premature optimizations, but just knowing, like we did here for SeaweedFS, where we noticed that this shouldn't be running except for debugging, right? So sometimes there is low-hanging fruit that you can there is something that you can quickly fix, and your performance will, in this case, it will double. So this is something that is very low effort and high gain. So make sure to learn how to use a profiler. There is one for Python, there is one for Java if you use Java, and now you know how to use it in Go. And there you have it. Now you know how to set up and benchmark all the popular open source object stores, which ones are most efficient for a single node setup, and how to profile your Go code to identify bottlenecks and improve performance. In the next video we'll cover identity and access management, IAM, explaining how we implemented minimal support for it on LabStore. Actually, I haven't started doing that yet. As usual, this week's blog post is available at datalabtechtv.com. Follow the channel on Blue Sky for updates, and join Discord if you have any questions. Don't forget to drop a like and subscribe for all things data. you.